Hey guys, welcome back to day 27. We're going to do Bonding Workbook 1 today. So first couple we're going to do is some Lewis structures of Ionic, and then we're going to move on to the covalent or molecular. So let's dive into the Lewis symbol of magnesium oxide. So we're going to do magnesium, oxygen, going to magnesium oxide. We know magnesium has 2 valence electrons. Oxygen happens to have 6 valence electrons. And so we know that these 2 purple electrons from magnesium are going to go to the oxygen. So we're going to roll oxygen first, because I'm already in the blue pen. And then we'll add the magnesium, valence electrons, and we're good. That's all the Lewis symbol is, right, to diagram the reaction between magnesium and oxygen. Okay, number 2. Number 2 is using the data provided, calculate the lattice energy of calcium chloride. So that's what we're doing, the lattice energy, calculating the lattice energy of calcium chloride. And it gives you a bunch of different data. So this is the Born-Haber cycle, if you remember. We have calcium, solid, plus Cl2 gas, going to CaCl2 solid. And if you remember, the first step in this is going to be step 1. We'll do step 1 will be sublimation. How do I know that? Well, we're talking about ionization energy of calcium. And ionization energy is the energy required to remove an electron from an isolated atom or ion in the gas state. So we have to go to calcium gas. The sublimation energy we're going to look for is right here. We've got this one and this one. So these 2. So it's 179.3 minus 0. So it's 179.3 kilojoules per mole. Then we're going to do 2 steps. We're going to do step, I want to change back to black. Step 1, or I guess step 2A, calcium plus gas. And step 2B, calcium 2 plus gas. So we have step 2. We got IE1 and IE2. The first ionization energy and the second. The first ionization energy is 590, and the second one is 1145. So I have 590 kilojoules per mole and 1145 kilojoules per mole. Chlorine has to go to 2Cl gas. Has to break the bond. So step 3, we got to break the bond. And the data we have is right here. So it's 2 times, because there's 2 chlorines, 121.7 kilojoules per mole minus 0. So it's 200 and, what is that, 43-ish overall. And then chlorine has to go to, we'll go all the way down to even, 2Cl minus. It has to gain an electron each. We're going to call that step 4. That's electron affinity. And the electron affinity for chlorine is negative 349. But there's 2 of them. And then last but not least is step 5, the lattice energy. And that's what we're calculating. So overall, the overall energy change delta HF standard of CaCl2, and we'll cover that in the thermochemistry chapter, will be equal to all the steps. Step 1 of sublimation, plus step 2, IE1 and IE2, plus step 3, which is the bond dissociation energy, the bond energy, plus step 4, the electron affinity, plus step 5, which is our lattice energy. So the lattice energy will equal everything minus subtracted from the delta HF of CaCl2. So let's put numbers in. Negative 795.8 kilojoules per mole will equal our sublimation of 179.3 kilojoules per mole plus 590 for IE1 plus 1145 kilojoules per mole for IE2 plus 2 times the 121.7 plus 2 times negative 349 plus my lattice energy. So now we can just put this into the calculator and solve for the lattice energy. And the lattice energy would be negative 2,256 kilojoules per mole. And sometimes I only had 3 sig figs. Well, actually, I only had 2 sig figs for some of them. So let's assume that the 590 is 3 sig figs. And obviously 0 is 0 because it's a standard value. So let's assume 3 sig figs at negative 2,260 kilojoules per mole. And that's how you get the lattice energy of an ionic compound. So that's the second example we've done. And I guess the good news, or bad news, is that this is too long to really be a test question. I don't know, maybe online, maybe a little different because it's online and there's resources, but in a seated class, I've never given this as a test. So that's all the ionic compounds we will be doing. Next are some covalent compounds. So we're going to draw the Lewis structures. We're going to talk about the electron pair arrangement, and that'll be in green. The shape in blue. The hybridization in, it'll be purple. The polarity, which will be red. Oh, that's orange. And if the molecule's resonance, I usually leave black. So first thing up, electrons in the molecule. 2 times 1 plus 2 times 6. So that would be 14 electrons. How is it arranged? Well, I don't know. I got H2O2. So you can play around to see, figure it out, but we want to minimize the formal charge and minimize, make sure everything follows the octet rule or duet rule. So let's try. H is not in the middle. The question then becomes, are the O's connected or are the H's and O on the central O? Is there one central atom or two? Question. Well, let's try 2. 2, 4, 6, 8, 10, 12, 14. Is that the best Lewis structure? Well, let's check. Let's check. 2 for hydrogen, good. 2 for hydrogen, good. Oxygen, 2, 4, 6, 8, good. 2, 4, 6, 8, good. Formal charge, 1, 2, 3, 4, 5, 6, good. 1, 2, 3, 4, 5, 6, has 6, brought in 6, good. Electron pair geometry, so both oxygens here. My electron pair geometry looks to be linear. No, it's not linear. Well, I drew it in a straight line. Doesn't matter. I have 2 pairs that are bonding and 2 pairs that are non-bonding. 4 pairs total. It's tetrahedral. Doesn't matter if I drew it in a straight line or not. Shape. 2 lone pairs, bent. The hybridization. sp3. Polarity. It is, yes, it is polar. Right there, bent oxygen. It's not symmetrical. And then there's no resonance because there's no other way to draw this, so there is no resonance. NH2OH. Electron count. Nitrogen is 5 plus 2 times 1 plus 6 plus 1. 7 and 7 is 14 electrons. How is this arranged? Ooh. Well, let's see. I have an N. I got 2 H's. H, let's say OH. Let's just try to do it like it's written. Let's see. 2, 4, 6, 8, 10, 12, 14. Is that good? Well, each H is good. Oxygen has 2, 4, 5, 6. Its formal charge is 0. Nitrogen, 1, 2, 3, 4, 5. Its formal charge is 0. They have 8 electrons total. I think that's good. Right, so I have 2 central atoms now. I have N and I have O. Electron pair geometries. 1, 2, 3, 4 pairs for nitrogen. Tetrahedral. Oxygen, 1, 2, 3, 4 is also tetrahedral. Shape. Shape of nitrogen, 1, 2, 3 pairs that are bonding, 1 lone pair. So it's trigonal, pyramidal. Oxygen would be bent. They're both sp3. Polar? Yes, this would be polar as a molecule. So the whole thing's polar, and then the whole thing has no resonance because we cannot draw them another way. ASO3, 3 should be 3 minus. Hopefully it's on your paper as 3 minus. Valence electrons. Arsenic has 5 valence electrons, plus 3 times 6 for oxygen, plus 3 more. That looks like it's 26 electrons. How's this laid out? Well, probably going to be arsenic in the middle. One, two, three. Let's see. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I got 2 extra on the central atom as 26. Perfect. Is that the best Lewis structure? Think about that. Electron pair geometry would be 4 pairs, tetrahedral. Shape is trigonal, pyramidal. because 4 pairs, 3 bonding pairs, 1 lone pair. Hybridization then, of course, is sp3. Polar, you betcha. Resonance. I'm going to put resonance down. It's unequivalent because the formal charge is changing. But I can minimize the formal charge here. It doesn't matter what oxygen. If I do that, now the formal charge of everything 1, 2, 3, 4, 5, 6. Oh, that's not good. Right? So now oxygen would be 1, 2, 3, 4, 5, 6. So arsenic would be -1, and that oxygen is 0. So that's probably not going to happen. You could do it, technically speaking, because oxygen has, or arsenic can double bond like that, but you don't need to. So I'm going to say there is resonance here. But for your purposes, at Pearson, there's probably going to be no. It'll probably be no in this situation because we're not changing the formal charge. But technically, there is resonance here. So that's the best structure. Number 4, H2SO3. So electron count. We have 2 times 1 electron plus 6 plus 3 times 6. So that's 26 electrons. How is this laid out? Well, S is probably in the middle. O, 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 H, H maybe? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. That's not good. Hard to see these. But this oxygen only has 2, 4, 6 electrons. I don't think this is good. Anything we can do? Well, sulfur has too many, but I can't take an electron pair away. So if this happens, what we need to do is put them together differently. So it's not just moving the electrons around, it's actually rearranging some atoms. Now this is a ternary oxyacid. And these oxyacids, H is bonded to O, bonded to Y, if you remember. So the H's are bonded to O's. A lot of times you'll see it written as this, O, 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 and then let's say an H there, let's say an H there, just for fun. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Is it the best Lewis structure? Technically not. Because sulfur has 1, 2, 3, 4, 5. We can double bond and make it as good as we can get. So now there's 2 central atoms. There's the S and then there's the O's. And both those are the same. So I have S and I have O. So the electron pair geometry for S, 1, 2, 3, 4 pairs, tetrahedral. Oxygen, 4 pairs, tetrahedral. Shapes. Sulfur as 1 lone pair, trigonal, pyramidal. Oxygen, 2 lone pairs, bent. Hybridization for both of them, sp3, because they're tetrahedral. Is this thing polar? Well, of course it is. Got top 5 bonded to sulfur, and it's asymmetrical. It's going to be polar. Lastly, resonance. If I can minimize formal charge, we have yes, unequal resonance. Because I can move this double bond back. I can move the double bond back to the oxygen, so it technically does have resonance. NO, Electrons. 5 plus 6 is 11. Bond. 2, 4, 6, 8, 10, 11. Not good. Let's see here. 2, 4, 6, 8. Good. 2, 4, 6, 8. 7. 7. 7. Ooh. Is that okay? Yeah, that's a radical. There's not much we can do about it. Now, there is another way we could do this, though. And, oh, I could do it this way. Where the radical is there. What's the difference between those two? The pink one has formal charge of 0 for everything. Here, +1 and -1. So formal charge is not minimized. So now, for the electron pair geometry, there's no central atom. So there's none. The shape, it still has a shape. Your shape is still linear. Hybridization is none, because our book says terminal atoms do not hybridize. Is this polar? Well, it's not the same atom, so yes, it's polar. And we're going to say yes to resonance. Yes, unequal resonance. So Chem 1, most of the times, they will tell you no, but technically there's unequal resonance. We'll just distinguish that later. Number 6. Electron count. 4 plus 2 times 1 plus 2 times 7. So it's 14, and 6 would be 20 electrons. Who's in the middle? Carbon. Let's put the CLs on opposite sides, H's on top and the bottom, and bond. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, is that a good Lewis structure? Yes. Electron pair geometry is carbon with 4 bonds, tetrahedral. The shape is also tetrahedral. Hybridization then is sp3. Polar. Well, it looks symmetrical, doesn't it? Except it's not. Just because we drew it, chlorine's on the same side. As if it's north, south, east, west, or up, down, left, right, that would look very symmetrical. The problem is those bond angles are 109.5 degrees apart. So they're not symmetrical. No matter what, I have 2 chlorines on the same side of carbon. So this will be a little bit polar. Let's use the right color. And of course, there is no resonance, all single bonds. And that will be it for this video. Stay tuned for Bonding Workbook 2. Take care, guys.